kind of stupid. But constant sequences limit to the, eventually constant sequences limit to the constant. And so there's a generic principle here that if you can prove something about the convergence of the tail of a sequence, like past a certain point, then that's true for the sequence. I mean, that's the limit. In other words, the flip side of this, of course, is that you could change a finite number of terms in the sequence, and it wouldn't change the limit. You can't alter a limit by just changing a finite number of terms in a sequence. Your textbook refers to this as the stability of the limit. Any questions? All right, so section 11.4 is entitled Some Important Limits. And I opted not to do that today because I feel like your brain might explode if I tried to do it today. Mine too. And so I'm going to put that off till tomorrow maybe. And we'll come back to that. The arguments in here are very, very beautiful and nice, and really using some of the things we talked about today, woven together to prove things which are not immediately obvious. Some of these things not immediately obvious. We'll come back to that though. So what I'm going to do for the remainder of the time is talk to you about L'Hopital's rule. All right. So just looking ahead this week, we should cover L'Hopital's rule and improper integrals. Right, and so I think by the end of this week, I will have pretty much lectured on everything that's on the test. But the homework's lagging a little bit, so I have to let you turn in your homework from up through 11.3 on Thursday, and then we'll have to have the later sections due next week sometime. I'm not sure what's a good day. I'll have to think about that. Hopefully there won't be snow. Yeah. Okay, so here's the deal. The limit of f of x over g of x is equal to the limit of f prime of x over g prime of x. And this is true either type 0 over 0 or infinity over infinity. I'm going to be greedy and state them both at once. So here this is L'Hopital's rule. It says you can take the limit of a quotient is the limit of the quotient of the derivatives, provided, of course, this is assuming what? The limit of f of x is equal to 0, and the limit of g of x is equal to 0, or, right, or infinity for both. So 0 over 0, infinity over infinity are examples of indeterminate forms, right? Zero over 0, infinity over infinity. There are more. But before I go on further about that, let me just speak a word more. Like limit, what do you mean lim? Lim, what's lim? Well, fine. Lim is a shorthand for a bunch of different cases. First of all, this could be the limit as x goes to like a for some finite a double-sided limit. It could be a single-sided limit from the left or from the right. Could be a limit at infinity. Could be a limit going to minus infinity. I believe those are all your flavor choices. I think that's every single last kind of limit we taught you in Calculus 1. Or you should have learned in Calculus 1. Anyway, all of these are covered by this L'Hopital's rule. Now the textbook, it has a proof of the 0 over 0 case using something called Cochise mean value theorem, I think. And I'll go over that some other day probably. The book refuses to prove the infinity over infinity case, all right, which is fine, like all of the calculus books do. And this theorem is true in more generality than the book is willing to state. It's in fact the case that if you do this rule and the, at least as far as I know, if the limit of the quotient of the derivatives like blows up, say this goes to infinity or something, it then actually means that this is also infinity. So in the cases that the limits don't exist but they misbehave in a certain way, then the original quotient also misbehaves in the same way. Like it's true in much more generality than your book states. Your book is very conservative in its statement of the L'Hopital's rules. And so I'm going to be greedy and claim it in its blinding generality, and I will refuse to prove anything about it. I hope you can forgive me for that, yes. Of course, yes. So I will get to that in just a second here, but that is a valid point. So of course we also have what? 0 times infinity, infinity minus infinity, and then you've got your 1 to the infinity, or infinity to the 0, or what's the other one? 0 to the 0, I think. Yeah. Is infinity a number? What does 1 to the infinity mean? When I say 1 to the infinity, what I mean is you're facing something like the limit as n goes to infinity, right, of 1 plus 1 over n to the n. If I slap an x here, by the way, this is e to the nx. Not 1. That has type 1 to the infinity, right? But that's not saying it actually is 1 to the infinity. It's something that's tending to 1, and it's something that's tending to infinity. This is a shorthand for a pattern that you see in the limit. It's not actually equal to 0 over 0. It's not actually equal to infinity over infinity. It's not equal to infinity minus infinity. It's not equal to 1 to the infinity. It's not equal to infinity to 0. It's not equal to 0 to the 0. And it's not you. It's me. I have an anger issue with this. Like, it angers me when I look at the test and then people write equals infinity over infinity. Like, just no. I mean, I am human. I do have certain pettiness, and if you anger me, I might take it out on you. I don't know. You never know. I try to restrain my. Try to not be mean, but okay. Let me get to the gentleman's question. Travis, I think. Yeah. So here's one limit. I mean, your question is valid, of course, right? Because we're using a notation that makes it look like we're doing arithmetic with infinity, but it's really a shorthand for certain patterns of limits. Here's one. Limit as x goes to infinity of x squared e to the minus x. All right. Now this guy is type infinity times 0. It is not equal to infinity times 0. That's nonsense. All right. Now this, on the other hand, is equal to the limit as x goes to infinity of x squared over e to the x. What did I do? It is known as algebra. This is L'Hopital's rule, type infinity over infinity. This is my notation. I write a script L through the equals, and I put under it infinity over infinity. This is not my notation. This was taught to me, if I recall correctly, by Dr. Lang. Dr. Lang worked for NASA before it was NASA. He had a PhD in topology, which is like some really, really pure math, okay? and went to work, and they told him, "Oh, we need you to calculate the fourth order Runge-Kutta for this trajectory." So the fourth order Runge-Kutta is a very dirty numerical method that you can use to approximate a solution to a particular kind of differential equation. And he said, "Sure." He said, "I'd never seen it before." Went to the library, got a book, I learned the fourth order Runge-Kutta. So, Dr. Lang. Dr. Lang was hilarious. I like Dr. Lang. What was NASA before it was NASA? No, it was something before it was NASA. It was, I don't remember, but whatever that was, he worked for it. All right, so. Yeah, I don't know. So you apply L'Hopital's rule once, and I guess what I'm saying is I got this notation from Dr. Lang. That was my point. 2x, although I don't think it's his either. I've seen this other places. 2x over e to the x. Not typically in textbooks because it's about impossible to typeset. Right. Like it's not in my notes either. I don't know how to make this happen in LaTeX.
They don't have a symbol for that? Like the next character?
Not like a script L through an equal sign? No. I'd have to build it. Haven't done it. It doesn't give me joy to do these sorts of things. All right. L'Hopital's rule, infinity over infinity. And see, it's still indeterminate is the point. So we do it again. And we get the limit as x goes to infinity of 2 over e to the x. Right, at this point, game over, it's 0. I like this topic to bookend today because what we were doing earlier was hard, but this, come on, this is not so bad, right? Here's another example. Oh, forget this example. This is the example I just did for you. Erase. Here's another example. Limit as x goes to infinity of x ln x. I mean, sometimes you don't need L'Hopital's rule. Sometimes it just blows up. Infinity times infinity is not indeterminate. It's just, it's just it. It is what it is. This one, on the other hand, if I have x goes to infinity of ln x over x, well, now we got something. This is infinity over infinity, L'Hopital's rule, 1 over x over 1, which of course gives me 0 again. You're starting to think infinity over infinity is always equal to 0 from my examples, right? Unfortunate. By the way, there's a theorem, and a lot of the reason we're talking about L'Hopital's rule right now is not so much that we're looking at infinite limits at infinity for continuous functions. In fact, this really, really, really is why we're looking at this right now, is we're going to use this like mad. If you have the limit as x goes to infinity of f of x is equal to L, then the corresponding sequential limit also goes to L. The difference between this and that, this is a statement about a continuous function. This is where we can do L'Hopital's rule. Over here, f of n, that's a sequence. I can't differentiate sequences, right? That's the trouble. But I can differentiate functions. So we get to use calculus and L'Hopital's rule to study functions which correspond to sequences whose limits we're interested in. This story is going to play out over and over and over again as we go on. Okay, so that's, I mean, there's an obvious question, like why all of a sudden are we looking at functions where we were looking at sequences before, right? This connection is why. All right, we should have at least one example that doesn't work out to 0, right? How much time do I have? Oh, man. If you watched the end of the previous lecture, there's one that works out to a half, if you really want to see it right now. Okay, so tomorrow I will go and do 11.4, hopefully. But before I do that, I will answer your homework questions. All right?